Hello, in this lesson we are going to learn some rules for calculating derivatives of power exponential and trigonometric functions without having to work through the limit definition of the derivative. We're going to start by looking at power functions. So a power function in general is a function in the form of y equals k times x to the power p, where k and x are real numbers. So you have a coefficient times x raised to a real number power. That's called a power function. And we have several examples of power functions here, like f of x equals x to the power 5, f of x equals x to the power 4, x to the power 3, x to the power 2, x to the power 1. Let's consider the derivatives of each of these power functions. And we know that we can find the derivative by using the limit definition of the derivative. So if you remember what that looks like, we are going to find the limit as h approaches 0 of f of x plus h minus f of x over h. So the first thing we would do is find f of x plus h by substituting x plus h into f of x, and that is going to give us this expression right here, x plus h to the power 5. Then we subtract the f of x, so we're subtracting x to the 5th and dividing by h. When we expand x plus h to the power 5, we get a lot of terms, and we want to combine any like terms that we have, like x to the 5th and negative x to the 5th, simplify as much as we can, and then factor in h from the numerator. Once we do that, we can eliminate the common factor. H will be a common factor in the numerator and the denominator. We can eliminate that, and then we get to this step here where we can find the limit as h approaches 0 by substituting 0 in for h. And we end up with a result of 5x to the power 4. When we start with f of x equals x to the 4th and we work through the limit definition of the derivative, we end up with a result of 4x cubed. When we start with x cubed and we work through the limit definition of the derivative, we end up with 3x squared. When we start with x squared, we end up with 2x. And when we start with f of x equals x, we end up with 1 for our derivative. So let's summarize those results in a table and try and identify a pattern. The derivative of x to the 5th is 5x to the 4th. And while I'm thinking about it, let me just share with you another notation. I don't know if we've seen this yet. If I want to indicate the derivative of x to the power 5, I certainly could say f prime of x. But if I want to be very specific, especially since all of these functions are named f of x, so it could get a little bit confusing if I just start referring to something as f prime of x, I could also say the derivative of x to the 5th by putting x to the 5th in brackets and then using a prime symbol outside of the brackets. So that indicates the derivative of whatever's in the brackets. So the derivative of x to the power 5 equals 5x to the power 4. And the derivative of x to the power 4 equals 4x to the power 3, and so on. And you may have noticed that whatever the original exponent was here, it turns into the new coefficient in the derivative. So in f of x equals x to the power 4, 4 is the original exponent, and in the derivative, 4 is the coefficient. Okay, and that pattern continues in each of these examples. You might also notice something about the new exponent in the derivative. When the original exponent was 5, the new exponent in the derivative is 4. When the original exponent was 4, the new exponent in the derivative is 3. When the original exponent was 3, the new exponent in the derivative is 2, and so on. Then it's 1, and then it's 0. We can think of 1 here as x to the power 0. And this is x to the power 1. So it looks like in the derivative, the new exponent is just 1 less than the original exponent. And that is exactly the pattern that will help us quickly find derivatives for power functions. So if I want the derivative of x to the power 6, the original exponent is 6. That's going to become the coefficient in the derivative. And then the new exponent is just 1 less than 6. So I do 6 minus 1 and I get 5. So the derivative of x to the power 6 is 6 times x to the power 5. And if we want the derivative of x to the power 13, it's going to be 13x to the power 12. Imagine how long it would have taken us to find the derivative of x to the power 13 if we were using the limit definition of the derivative. We would need to take x plus h, that quantity, and raise it to the power 13. There would be lots and lots of terms there that we would have to manage. So this is a very quick and easy way to find the derivative for power functions, and this is called the power rule. Power for power function. So here's our power rule. For any non-zero real number, if f of x equals x to the power n, then f prime of x equals n times x to the power n minus 1. Okay, so we see exactly the same pattern that we just looked at. The original exponent becomes the coefficient in the derivative, and then the new exponent is just 1 less than the original exponent. So if f of x equals x to the power 12, f prime of x equals 12x to the power 11. And if f of x equals x to the negative 1, then f prime of x equals negative 1. We bring down the exponent, make it the coefficient in the derivative, and then we decrease the exponent by 1. So negative 1 minus 1 is negative 2. We typically don't leave negative exponents in our answer. It's not incorrect. It's just not considered to be in simplified form. So to rewrite this without negative exponents, we would say negative 1 over x squared. If f of x equals x to the power 1/2, then f prime of x equals, let's bring down the exponent, make it a constant multiple, 1/2 x, and then we're going to decrease the original exponent by 1. So 1/2 minus 1 is negative 1/2. Let's simplify that so that we don't have a negative exponent. It would be 1/2 times 1 over x to the 1/2. And x to the 1/2 can be rewritten as the square root of x. So I can also write 1 over 2 square root x. The original function f of x equals x to the 1/2 can also be written as the square root of x. And so I highly recommend that you memorize that the derivative of the square root of x is 1 over 2 root x. If you don't have that memorized, it's okay. You can derive it just like we did here using the power rule. You would, if you see the square root of x in the problem and you're trying to take the derivative of it, you convert it to x to the power 1/2. You apply your power rule. You simplify it so that there's a positive exponent, and then you rewrite it using radical notation instead of rational exponent notation. So that's kind of a lot of work, and you're dealing with negative exponents, and you have to do quite a bit of algebra to simplify this here. It's much easier to just memorize that the derivative of square root of x is 1 over 2 root x, because this is a derivative that we are going to be taking over and over and over again throughout this course. Let's look at another derivative rule, and this one is called the constant rule. So this rule tells us how to take the derivative of a constant. So constant function would be something like y equals 2. A constant function is a power function, right? It's a special kind of power function where x is being raised to the power 0. We just don't see that because x to the power 0 equals 1. So you could get away with applying the power rule here, but there's a much quicker result. And we can also think about this graphically. A constant function, when you graph it, just looks like a horizontal line. And what is the slope of a horizontal line? Well, the slope of a horizontal line is 0 everywhere. For all values of x, the slope will be 0. And we know that our derivative represents the slope of the original function. And so the answer should just be 0, and that is exactly what we see here. For any real number c, if f of x equals c, then f prime of x just equals 0. Okay, that is the constant rule. The derivative of a constant equals 0. So the derivative of square root of 3 is 0. The derivative of 4/5 is 0. The derivative of negative 3 is 0. Those are all real numbers. And when you take the derivative of a real number, you get 0. Our next rule is the exponential rule. So we want to take care not to confuse an exponential function with a power function. They can look pretty similar. A power function is going to be in the form of y equals x to the power p. Okay, and there might be a coefficient in front. I think before I said k times x to the power p. Yes, that is also a power function. K times x to the power p. But an exponential function is going to be of the form y equals, and we might have a coefficient in front, so we'll go ahead and put the k there. But instead of x to the power p, this time it's p to the power x. So with a power function, the variable is in the base, and your exponent is a number. In an exponential function, your base is a number, and your exponent is a variable. Okay, so it's different. Y equals x to the power 2 is a power function. Y equals 2 to the power x is an exponential function. Very important difference there. So this rule is for exponential functions. For any positive real number a, if f of x equals a to the x, then f prime of x equals a to the x times the natural log of a. Let's look at a couple examples. If f of x equals 2 to the power x, so in this example, the a value is 2. That's the base, right? So if we apply our formula, f prime of x equals 2 to the power x, just the same thing that you started with. If you're taking the derivative of 2 to the x, it's 2 to the power x times, and then you take the natural log of the base. So 2 to the power x times the natural log of 2. If we start with f of x equals 5 to the power x, then the derivative, and I'm just going to mix up our notation here, 5 to the power x prime. So the derivative of 5 to the power x equals 5 to the power x, it's just the same thing, times natural log of the base, so natural log of 5. Now how about f of x equals e to the x? Here the base is e. The derivative of e to the power x equals e to the power x times the natural log of e. And what is the natural log of e? The natural log of e is equal to 1. So we usually just say e to the x. Okay, so that's probably the easiest derivative rule of all the rules we're ever going to look at. The derivative of e to the x is e to the x. It is its own derivative. Our next rule is the constant multiple rule. So constant multiple rule is not the same as the constant rule. You use the constant rule if you're taking the derivative of a constant. But a constant multiple means you have a constant multiplied by something else. That's not a constant. So if c is any real number and f is a differentiable function, remember differentiable means you can take the derivative of it. So c is a real number, f is a differentiable function, then the derivative of c times f of x is equal to c times the derivative of f of x. So what happens when you have a constant multiple inside of your derivative, you can bring it outside of the derivative and it's still a constant multiple. You multiply the constant times the derivative of the function. So I like to think of it as just moving that constant multiple to the outside. For example, if we want to find the derivative of 2x, we know that it's just going to be 2 times the derivative of x. I'm going to use this notation for the derivative of x. In fact, let me write it like this. The derivative of 2x equals 2 times the derivative of x. Like that. So we can take the derivative of the function part and then multiply the answer by the constant multiple. The derivative of x is 1. So this is just equal to 2 times 1, or 2. Number 2, f of x equals the square root of 3 times x. So the derivative of the square root of 3 times x, the square root of 3 is a constant multiple. So I can bring that outside, and it's going to be a constant multiple times the derivative of the x. The derivative of x is 1. So this is root 3 times 1, or just root 3. The derivative of 4/5 x is 4/5 times the derivative of x. And the derivative of x is 1, so 4/5 times 1, 4/5. Another way to think about these examples, they're all linear functions, right? And in a linear function, we know the derivative is just the slope of the linear function. So the derivative should just be the slope, which is the coefficient of x. So it's 2, and it's root 3, and it's 4/5. The sine and cosine rule. If f of x equals the sine of x, then f prime of x equals the cosine of x. If f of x equals cosine x, then f prime of x equals negative sine x. So you want to remember, this one you absolutely need to memorize. The derivative of sine x equals the cosine of x. And then the derivative of cosine x equals negative sine x. Now, if you're wondering why that is, why is the derivative of sine x equal to cosine x, we can always rely on the limit definition of the derivative to show that, right? We could say f of x equals sine x, and then f prime of x equals the limit as h approaches 0, f of x plus h. So sine of x plus h minus f of x, which is sine x, over h. Then we can use trig identities to simplify this. There is a trig identity that would allow us to rewrite the sine of x plus h in a different way. And then we would simplify, find the limit as h approaches 0, and we would end up with the cosine of x. But using that trig identity and then simplifying it takes quite a bit of work. So it's much easier if we memorize that the derivative of sine x is cosine x. So for the following examples, we're going to have to combine this rule with the constant multiple rule. We know that the derivative of 5 times the sine of x is equal to 5 times the derivative of the sine of x. And the derivative of sine x is cosine x, so it's equal to 5 cosine x. So we're combining different derivative rules here. The derivative of 3 cosine x would be 3 times the derivative of cosine x. And the derivative of cosine x is negative sine x. So we end up with negative 3 sine x. And the derivative of negative 2 sine x. Negative 2 is a constant multiple, so it's negative 2 times the derivative of sine x. The derivative of sine x is cosine x, so we end up with negative 2 cosine x. So let's practice finding the derivative using our various rules that we've talked about so far. If f of t equals pi, then the derivative, and we are asked to use proper notation, the derivative of f of t, we can write f prime of t. F prime of t equals, well, what's the derivative of pi? Pi is a real number, and this is a constant. It's not multiplied by another function. It's just a constant, and so we'll use the constant rule. The derivative of a constant is 0. The derivative of pi is 0. Part B, g of z equals 6 to the power z. That is an exponential function, so we're going to use the exponential rule. G prime of z equals 6 to the power z times the natural log of 6. H of w equals w to the power 3/4. That is a power function, so we're going to use the power rule. H prime of w equals 3/4 w. Now I'm going to subtract 1 from the exponent, so 3/4 minus 1 is negative 1/4. If we want to write that without the negative exponent, 3 over 4w to the 1/4. Part D, m of t equals 1 over t cubed. We're going to rewrite this before we take the derivative. 1 over t cubed can be rewritten as t to the power negative 3. And I'm going to write it this way so that it's in that power function form so I can use the power rule. So m prime of t equals negative 3t to the negative 4. Remember, we're going to subtract 1, so you have to be careful when your exponent is negative. Have a negative number and then subtract 1 from it. So we end up with negative 3t to the negative 4. If we simplify that so that we don't have a negative exponent, it would be negative 3 over t to the power 4. Part E, p of x equals 3 to the power 1/2. 3 to the power 1/2 is the same as the square root of 3. That is a constant. So we'll use the constant rule. The derivative of a constant is 0. So p prime of x equals 0. R of t equals the square root of 2 to the power t. That is an exponential function. So we'll use the exponential rule. R prime of t equals square root of 2 to the power t times the natural log of the square root of 2. In part G, we're seeing a new notation. This notation is the same as the bracket notation. This is telling us to take the derivative of what's inside the parentheses. So derivative of q to the power negative 1. If I want to use the bracket notation instead, I put q to the negative 1 in the brackets because that's what we're taking the derivative of. Remember that in the denominator, this is Leibniz notation. This is just defining what the independent variable is. So we're taking the derivative of q to the power negative 1. That is a power rule situation. So we're going to bring down the power, negative 1 times q, and then the new power is going to be 1 less. So negative 1 minus 1, negative 2, or negative 1 over q squared. If f of x equals negative cosine x over 4, let's rewrite this before we take the derivative. Dividing by 4 is the same as multiplying by 1/4. So this is the same as negative 1/4 cosine x. And the reason I like to write it that way is because now I can see I have a constant multiple of negative 1/4 times a function cosine x. So I know my derivative, f prime of x, is going to have the same constant multiple, negative 1/4, and then I just multiply that by the derivative of the cosine of x. And the derivative of cosine x is negative sine x. I have a double negative here. So it ends up being positive 1/4 sine x. Our next rule is the sum difference rule. If f and g are both differentiable functions, then the derivative of f plus or minus g is equal to the derivative of f plus or minus the derivative of g. In other words, we can combine our functions together first and then take the derivative, or we can take the derivative of each term separately and then combine the answers. The way that works in example number 1, we have a function equal to 2x plus 5. If I want to take the derivative of 2x plus 5, I can simply take the derivative of 2x and add that to the derivative of 5. So it's really just allowing us to take the derivative of each term individually. The derivative of 2x is 2, and the derivative of 5 is 0. So my final answer is 2 plus 0, or just 2. For number 2, if we want the derivative of root 3 x plus x cubed, we can use the sum difference rule and say, oh, that's the derivative of square root of 3 times x plus the derivative of x cubed. The derivative of square root of 3x is square root of 3. We use the constant multiple rule there and the power rule to take the derivative of x. Plus the derivative of x cubed. We're going to use the power rule there. The derivative of x cubed is 3x squared. So my answer would be the sum of those two results, square root of 3 plus 3x squared. And in our last example, f equals 4/5 x minus 1. So the derivative of 4/5 x minus 1 is the derivative of 4/5 x minus the derivative of 1. The derivative of 4/5 x is 4/5, using the constant multiple rule there and power rule, minus the derivative of 1. The derivative of 1 is 0. And so my final answer is just 4/5. For these next examples, we might have to do a little work algebraically to get the equations into a form where we can use one of these derivative rules that we've learned. For the first example, f equals x to the power 5 over 2 minus x to the power 4 plus 2 to the power x. That's already in a good form. We can take the derivative of x to the power 5 halves using the power rule. So f prime of x equals 5 over 2 times x, then we subtract 1, so we're subtracting 2 over 2, which gives us x to the power 3 over 2. That's the derivative of the first term, minus the derivative of the next term, so the derivative of x to the fourth is 4x cubed, plus the derivative of 2 to the power x. Here we're using the exponential rule. So plus 2 to the x times the natural log of 2. And that will be our final answer. For part B, g of x equals 14e to the x plus 3x to the power 5 minus x. Each of those terms is already in a form where we can use one of these derivative rules. So we are good to go. G prime of x equals the derivative of 14e to the x. We're going to use the exponential rule combined with the constant multiple rule. 14 is a constant multiple, so it will remain a constant multiple in the derivative, and the derivative of e to the x is e to the x, plus 3x to the power 5 is a power function. We're going to use the power rule along with the constant multiple rule. So we're going to often see our power functions with coefficients other than 1 in front. Normally, if it was just x to the fifth, we would say bring down the 5 and make 5 the coefficient. Well, yes, we're going to do that, but there is also a constant multiple of 3. So the 5 comes down and it gets multiplied by the 3. Because remember, 3x to the fifth prime equals 3 times x to the fifth prime. So 3 times 5x to the fourth. You end up multiplying the 5 when it comes down by the 3. So the 5 comes down, times 3 is 15x, and then you reduce the power by 1. So the new exponent is 4. Minus the derivative of x is 1. We're using the constant, no, we don't need, well, we sort of need the constant multiple rule, maybe. You can think of it as the sum difference rule as well. But the derivative of x is 1. Now for the next problem, we're going to have to rewrite this before we can take the derivative of the first term or the second term, unless you've already memorized from an earlier problem we talked about the derivative of the square root of z. If you do have that memorized, because we did this early on, where was that? That was pretty early on, right here. The derivative of square root of x is 1 over 2 root x. So the derivative of square root of z is 1 over 2 root z. Now, if you didn't remember that, you could rewrite the square root of z as z to the power 1/2 and apply the power rule. You'd get 1/2 z to the negative 1/2, and then you'd have to rewrite that as 1/2 times 1 over z to the 1/2. And then you would write that as 1 over 2 root z. Okay, so that's a lot more steps to think about than just 1 over 2 root z. Let's move on to the next term. To find the derivative of 1 over z to the power 4, we need to rewrite this as z to the power negative 4 so that we can use the power rule. the derivative of z to the power negative 4 is negative 4z to the negative 5. So typically when I'm doing this, I would just change that plus to a minus, and then 4z to the negative 5. And we can rewrite that as 4 over z to the 5th, which we'll wait and do in a moment. 5 cosine z, constant multiple rule, so plus 5, times the derivative of cosine z. The derivative of cosine z is negative sine z. So I need to make this sign negative. Okay, and there we go. If I want to simplify, 1 over 2 root z minus 4 over z to the power 5 minus 5 times the sine of z. All right, let's erase this to make some room because we're going to have to simplify part D algebraically before we can take the derivative. Y squared plus 1 times y squared minus 1. We have not talked about any kind of derivative rule that allows you to multiply. We had the sum difference rule, where if you have a bunch of terms added together, you can just add their individual derivatives. But we have not seen a rule that says you can multiply derivatives together. That's not how products work. When we want to take the derivative of a product, that is not going to lead to the right answer. So we want to actually multiply this out first. If we expand y squared times y squared times negative 1, 1 times y squared, 1 times negative 1. So we get y to the 4th minus 1 is equal to s of y. So the derivative, s prime of y, now it's easy to take this derivative. We use the power rule on the first term and the constant rule on the second term. The derivative of y to the 4th is 4y cubed, and the derivative of negative 1 is 0. So s prime of y equals 4y cubed. For part E, we also need to simplify before we take the derivative. We have not seen any kind of derivative rule that would allow us to divide two derivatives. You cannot just divide two derivatives. It does not work that way. So we're going to have to simplify this algebraically first. There's a couple ways to do that. We can take the numerator and multiply it by x to the negative 1. In other words, move this term up to the numerator and make it x to the power negative 1. Now you can distribute x to the power negative 1. So when you multiply two numbers with the same base, you add their exponents. So you would get x to the power 3 minus 1 minus x to the power 0, because this is to the power 1, plus 2x to the power negative 1. And we haven't taken the derivative yet. We're just simplifying the original function. Now, though, you could take the derivative. It's in a form where we can just use power rule here. This isn't typically the way I like to simplify these, but some students prefer to do it that way, so I wanted to show you. What I prefer to do instead is to separate this into 3 fractions. We can have x cubed over x minus x over x plus 2 over x. So we separate that into 3 fractions. X cubed over x minus x over x plus 2 over x, which is equal to x squared minus 1 plus 2 over x isn't very helpful when I need to take the derivative. I would rather write it as 2x to the negative 1. I'm going to bring that x up to the top, the numerator, move it up into the numerator, and give it a negative exponent when you move it up into the numerator. Okay, now it's in a good form for me to be able to take the derivative. If this is q of x, then q prime of x equals the derivative of x squared, use your power rule, is 2x. The derivative of negative 1, use your constant rule, is 0. And the derivative of 2x to the power negative 1, use your power rule with your constant multiple rule. The negative 1 comes down, gets multiplied by the 2, and then x gets, the exponent gets decreased by 1. So it'll be x to the negative 2. And if we simplify that, it's 2x minus 2 over x squared. That's the final answer for q prime of x. Okay, let's find the slope of the tangent line to h of z if h of z equals the square root of z plus 1 over z at the point where z equals 4. So first, let's figure out what h of 4 is. When we want to write the equation of the tangent line, we need to know two things, h of 4 and h prime of 4, because our tangent line equation is y equals h of 4 plus h prime of 4 times x minus 4. That's what our tangent line equation is going to be. So we need to figure out what is h of 4, what is h prime of 4. For h of 4, we substitute 4 into h of z. So it's the square root of 4 plus 1 over 4, or 2 plus 1 over 4, or 9 over 4. H prime of 4. Well, before we can find h prime of 4, we need to find h prime of z so that we can then substitute the 4 into h prime of z. H prime of z is the derivative of h of z. So let's take the derivative of square root of z, 1 over 2 root z, plus the derivative of 1 over z, negative 1 over z squared. Both of these derivatives here are very helpful to just memorize. If you keep a list going of derivatives you should memorize, square root of z is definitely on the list. Derivative of square root of z, 1 over 2 root z. Sorry, if you're making a list, you should probably use an x, not a z. It doesn't really matter, but it's probably easier to just be consistent in all of your derivative rules that you're writing down. So the derivative of square root of x, 1 over 2 root x. The derivative of 1 over x, negative 1 over x squared. Those are both really helpful to memorize because we use them frequently. Both of those, if you don't memorize them, you can derive them using the power rule. Now that we know h prime of z, we can get h prime of 4. So h prime of 4 is 1 over 2 root 4 minus 1 over 4 squared, or 1/4 minus 1/16, or 3 over 16. And now that we have h of 4 and h prime of 4, we can write our tangent line equation. It's y equals 9 over 4 plus 3 over 16 times x minus 4. Writing the equation of a tangent line is something that we're going to continue to do throughout this course. Okay, quick check for understanding here. If a plus b squared equals 3, what is dA over dB? This is Leibniz notation. This is the same thing as a prime of b, like that. B is the independent variable. It's like the x. Think of that like the x, and think of that like the y. dA over dB, it's saying take the derivative of a with respect to b. So this would probably be easier if we solve the equation for a. A equals 3 minus b squared. So this is like a y equals something in terms of x, right? Now the derivative of a with respect to b is, I'm just going to write a prime, equals 3 minus 2b. We're using our power rule. Oh no, I made a mistake because the derivative of 3 is 0. The derivative of 3 is 0. The derivative of negative b squared is negative 2b. Negative 2b. So it can get a little confusing when we change up the letters from a standard x and y, but that is often going to happen. So we want to practice using all kinds of different notation with derivatives that we might encounter. If f of x equals x times x plus 5, then what is f prime of x? Well, again, we don't have any rule that allows us to multiply two derivatives together. Don't do that. Don't find the derivative of x and the derivative of x plus 5 and multiply them together. That's going to give you a wrong answer. What we need to do is simplify this or write it in a different way to where it does fit one of the derivative rules we already know. So you can here distribute the x f of x equals x squared plus 5x. And now we have derivative rules that we can use here. The derivative of x squared is 2x, and the derivative of 5x is 5. So 2x plus 5. If f equals x squared plus 3 over x, what is f prime of x? Okay, so we're going to, just like in the last problem, take the derivative of each term separately. That's our sum difference rule. The derivative of x squared is 2x. We write f prime of x. The derivative of 3 over x, okay, so you can do this the long way. Rewrite 3 over x as 3x to the negative 1, then use the power rule. It's negative 3x to the negative 2, and then simplify it, although in these answers it has not been simplified. So this isn't really the long way in this case. Be minus 3x to the negative 2, which matches choice A. What I was going to say is you can also think of 3 over x as 3 times 1 over x. And if you've memorized that the derivative of 1 over x is negative 1 over x squared, then you just need to multiply it by 3 because of the constant multiple rule. So that would be the derivative, negative 3 over x squared. Which is the equation of the line tangent to y equals x squared when x equals 4? Tangent line equation at x equals 4. We need to know, I like function notation here. It's easier to talk about different parts of the function. So f of x equals x squared, I know that I need to find f of 4 and I need to find f prime of 4. Those are the two things I need in order to write the equation of the tangent line. So to find f of 4, I just substitute 4 into f of x. F of 4 equals 4 squared, or 16. To find f prime of 4, I first have to take the derivative of f of x. So f prime of x, the derivative of x squared, is 2x. So now f prime of 4 is 2 times 4, or 8. So f prime of 4 is 8. When I write my tangent line equation, it's y minus the y-coordinate equals, oh, that's not the y-coordinate, y minus the y-coordinate equals slope times x minus the x-coordinate. And then sometimes, not always, but in this case we need to add that constant term over to the other side. So y equals 16 plus 8 times x minus 4. And because that's not an exact match, we're going to have to do some simplifying to figure out what is the right answer. So we'll just distribute the 8, and we get 16 plus 8x minus 32. So it's 8x. 16 minus 32 is negative 16. So 8x minus 16. And our last question, find the equation of the line that is tangent to g of x equals 2e to the x at x equals 1. So again, we need g of 1. We need g prime of 1. G of 1 is going to give us the point of tangency. G prime of 1 is going to give us the slope of the tangent line. Okay, very important to remember that when you're working on writing the equation of a tangent line. This is going to give us the point of tangency, and this is going to give us the slope of the tangent line. We have to find those two things. So g of 1 we're ready to find right away. Just substitute 1 into g of x. G of 1 equals 2 times e to the power 1, or 2e. Okay, that means the point of tangency is 1 comma 2e. Then we want to find g prime of 1, but first we have to find g prime of x, so we have something to substitute the 1 into. G prime of x is the derivative of 2e to the x. So constant multiple rule, 2 will be a constant multiple in the derivative, and then the derivative of e to the x is e to the x. So g prime of 1 equals 2e to the power 1, or 2e. Coincidentally, the same thing. G of 1 and g prime of 1 are both equal to 2e. That's just a coincidence. So our tangent line equation now is y minus the y coordinate, or we can add it to the other side. So y equals the y coordinate, which is right here, plus the slope, which is right here, times x minus the x coordinate. And that doesn't match one of the answers, so we're going to simplify this. This is equal to 2e plus 2ex minus 2e. And we have some like terms. 2e minus 2e is 0, so this all simplifies to just y equals 2e to the power x. Oh, that's not one of our choices. Oh, because I didn't write that correctly. Sorry, right here, where I was distributing, I wrote 2e to the power x, but it really should have been 2e multiplied by x. Like that, 2ex. So y equals 2ex is the equation of our tangent line. All right, we talked about a lot of derivative rules in this lesson, but hopefully you can appreciate how awesome these rules are because they allow us to find the derivatives without having to set up that limit definition and work through it. Think about how long it takes to do those limit problems where we're looking for the derivative. So I probably did this more quickly than you were able to do in your head along with me, but with practice you will be able to do that just as quickly as I did. Thanks for joining today. I will see you guys next time.